Thank you all. Hello all. Thank you for joining us in this webinar. I'm Kishan Joshi, the chair of San Francisco Bay Area chapter of PELS, and it gives me immense pleasure to continue bringing more power to 2022 with this webinar. Here's a little bit about our chapter. Recently, we were the recipients of the 2022 Santa Clara Valley Outstanding Chapter Award, the 2017 Region 6 Outstanding Chapter Awards, along with the 2017 PELS Best Chapter Award. Today's talk is on disturbance-free built-in self-test by Dr. Bertan Bakkaloglu, on-semi endowed professor at Arizona State University. Thank you, Professor, for presenting this talk.
Thank you for your invitation.
I would like to thank the support from our wonderful IEEE co-sponsors who helped to spread the word around and helped us in bringing forward these webinars. The PELS Milwaukee chapter and UC Berkeley PELS PES IAS chapter. There's a lot of work that goes on in the background in organizing events and bringing initiatives to our membership. And I would like to thank the support from the excellent team of officers and volunteers from the PELS San Francisco Bay Area chapter. None of this would have been possible without their support. Also, do not forget to check out our new website, which has a bunch of talks, the PDF slides, and the YouTube videos for those posted on the website. You can find those in the archive section. And you can also follow us on Twitter at sfbac_pels for more updates. If you'd like to be in loop on all the great talks and events happening, then IEEE eGrid delivers all of that info to your inbox for free twice a month. So be sure to register at the link shown here on egrid.biz. So thank you for being here. The PDF slides and the recording of the webinar will be uploaded to the archive section. Thank you to our speaker for graciously accepting for the recording and uploading. Now, a little bit about our speaker today. Bertan Bakkaloglu received his PhD from Oregon State University in 1995. He joined Texas Instruments Inc. Mixed Signal Wireless Design Group in Dallas, Texas, working on analog, RF, and mixed signal fronts for wireless and wireline communication ICs. He worked on system-on-chip designs with integrated battery management and analog baseband functionality as a design leader. In 2004, he joined Arizona State University Electrical Engineering Department in Tempe, Arizona, as an associate professor. He is currently the on-semi endowed professor, and his research interests include RF and PA supply regulators, high-efficiency DC-DC power converters, linear regulators, low-noise power management circuits, biomedical instrumentation circuits and systems, high-speed data converters, and built-in self-test circuits for analog ICs. Dr. Bakkaloglu has been a technical program chair and general chair of the IEEE RFIC conference and an associate editor of the IEEE Transactions on Circuits and Systems and IEEE Transactions on Microwave Theory and Techniques. He is the founding member of IEEE Solid State Circuit Society Phoenix chapter and Microwave Theory and Techniques Society RFIC's TC23 subcommittee chair. He is an IEEE fellow and member of the National Academy of Inventors. Without further ado, I would like to hand over the stage to Bertan.
Thank you, Kishan. Thank you so much for the introduction. So today's talk, as some of you may know, part of my research interest is integrated DC-DC converters and linear regulators. However, today's talk is mostly more generic in the sense that it will be talking about system identification and that would enable built-in self-test of power converters. It's more system-oriented, but it does have an IC-level implementation that I will be sharing with you as well. For those of you who might be interested in high reliability applications where you want to track the progress or degradation in DC-DC converters or external components, this may be of some use. This work was in part funded by JPL, NASA, and quite a few of my students worked on it, as you'll see. And the main idea is early detection of degradation, aging, and failure. in high reliability power delivery system. Most of the dynamic voltage scaling schemes these days are going up to higher and higher switching frequencies. That means the component size values are reducing. That means the variations associated with the component size have a bigger impact on overall performance of DC-DC converters. On this page, you see some of the aging in terms of various different type of dielectric capacitors and sizes, and dielectric chemistry, so to speak. And also their degradation with DC bias. In some cases, within 1,000 hours of use, capacitors can degrade by up to 10%. In the case of X7R Y5V, you can see the degradation can be even more. And on top of that, obviously, temperature would be another additional problem. And on this page, you see some of the temperature effects and bias effects, combined temperature and bias effects as well. And another one is the ESR. In LDOs, as some of you may be familiar, we depend on ESR for stabilizing the system, and also they depend on temperature as well at different frequencies. Therefore, several systems that has multiple levels of hierarchy would benefit from some kind of monitoring and communication with respect to their health. This is a very suitable system. There's an intermediate bus converter followed by POLs. Both IBC intermediate bus converter as well as POL would benefit from some kind of system tracking. These type of systems employ multiple converters. They're in series. Many of them are switch mode. The interaction between them is critical. Also, component variations can make the system go unstable at various different points of the power management tree. Health monitoring is therefore quite helpful. But what's the gold standard for checking the small signal stability? The gold standard is loop analysis, but it's costly. That's why we can not only on automatic test equipment ATEs, also on the bench. It requires some kind of an impedance analyzer to break the AC loop and try to get the system phase margin, gain margin, and any kind of degradation. It involves insertion of a test signal and measurement through a loop break. So if we want to do a built-in self-test for a converter, frequency response, small signal frequency response is a good starting point. Instead of using expensive hardware, can we do this not only during production, but also during for calibration during regular use? In this regard, built-in self-test circuitry for frequency response measurement is valuable. So the end result would be health monitoring based on changes in the AC response, which includes external and internal components, and pinpoint and locate the faults in the system by looking at the signature associated with various component degradations. And ultimately the circuit that needs to be used for that also needs to be robust. What happens during PVT variations, and what type of degradation to expect? During overstress conditions, during capacitor and ESR changes, as you can see, overshoot, sometimes ringing, during load dumps would be changing, and from its linearized AC response, the phase margin and gain margin would be also degraded. These results in obviously higher over and undershoots, and it can cause a cascade of load failures. And if there's any drift in terms of threshold voltage in the powertrain, compensation network changes, amplifiers and linear stages that are being used in the system also will degrade, and it will change the frequency response. So moving on, now that some of the baseline issues associated with aging and degradation is established, I'd like to start with some of our nomenclature and definitions. For those of you who are in testing, it's obviously a very well-known, these are well-known terminology, but for those of you who may not, online means system is operational, closed loop, supplying the load without loss of regulation. The term online is also being used for all kinds of analogs or sub-module and system self-test as well. So our goal is to make it online, obviously. In field, which obviously, as the name implies, techniques capable of operating while it's deployed. This is another desired feature if there's a host processor that can read out the data and do advanced calibration, or if there's triple redundancy, for example, using backup converters. Parametric system identification is for the system to be identified as parameterized into a known system model. What's a known system model? For example, a PWM or even a synchronized hysteretic converter. It's a well-known, well-established second-order system model with some compensation. And parametric means basically sensing the pinpoint and sense the certain parameters of the closed-loop system. Or on a state space model, basically estimating the entries in the state space model matrix. Non-parametric SI does not assume any particular structure. That's another approach for complex systems where there is no single governing state space representation. And that's quite valuable, like I said, in complex systems. And model reference is comparing the results using the system identification methods to a known system model to detect and diagnose changes. So model reference, whenever we refer to that, for example, model reference control is also another term used. Basically, you have a known parametric system and you try to detect and diagnose the changes. So what do we do in order to estimate a spectral or closed loop AC response of a system? So the most intuitive method is obviously a swept sine wave. You generate multiple tones and pass through a system under test, whether it's closed loop or open loop, in certain points, and look at the peak-to-peak value of the signal that passes through. And in this example, let's say it's a bandpass. It's a low-pass system. We go through a bandpass filter to clear up all the harmonics, because it can generate harmonics, especially in PWM mode. It will be generating harmonics related to intermodulation distortion products, and get the AC response out of it. It requires a D2A converter, a digital frequency synthesizer. It's computationally intensive if FFT is being used, and IC level implementation is quite hard, and also it generates tone. If you want to do this on a closed loop sense, you don't want to show tonal content showing up. The other method is cross-correlation based techniques. In a way, it generates a partial random bit sequence which emulates a white noise. Being partial random, we can extract the system's response to this white noise by correlating the response of the system with respect to the partial random bit sequence, that PRBS bit sequence that excites the system. This is a well-known system identification approach. The input signal is a zero mean, white, hopefully, noise system, and the sample per sample cross-correlation of the input and the system response is ultimately if generates the impulse response of the system. You can think of it this way: if it was a broadband system with no delays, no phase delays, or no AC response, by cross-correlating a PRBS sequence by itself would only give you an impulse. But if the system has a finite impulse response, it extracts the impulse response. At that point, what's represented as h of n here will have lots of characteristics that closely relates to phase margin, gain margin, and AC response of the system. But you can also go through a power spectral density estimator or an FFT engine to get the frequency response as well. And as you can see, this is quite an old technique, and it was initially deployed in 1970s. Has this been done before for overall for analog systems. I mean, it has been used for analog systems in general. Analog test problem. This can be filters, A to D converters sometimes. It has been used on linearized systems. The other approach was open loop built-in self-test. It's basically using a full-blown A to D in order to converter, but it required open loop operation, so it means it cannot be done during regular operation. And the cross correlation was after a full digitization of the full response of the converter. That means if, for example, your PRBS sequence is coming in, let's say, a megahertz, and the response is obviously in the range of megahertz, that needs to be oversampled by at least 10 to 20 so that you get all the characteristics of the analog response. What's coming out is basically an analog response of the system. The third one is both direct impulse and PRBS together. Here, ultimately, an impulse is being injected into, for example, digital pulse width modulator engine. It does require an A to D converter as well, and it has limited loop bandwidth. A to D converter is quite coarse in this scheme. This is already a digital converter, so the A to D converter in the feedback loop is almost kind of free. All right. So far, let me just quickly go over this. So far, what we've seen is you can do a swept sine wave. It is accurate, but integration is tough and it generates tones. Mixed signal approach is accurate, but we don't want to use a full-blown A to D converter in the feedback loop. Open loop is also accurate, but obviously it's open loop and it's not operational. Closed loop BIST for digital is suitable, but it requires a digital converter. Ultimately, because of the digital converter's bandwidth, it has a limited bandwidth. So what we need is a multi-level, multi-period PRBS. The output should be, white. The input and the response of the system should be white noise. And as we sample the system at the output, we should be able to digitize and find the response of the system. Ours is also not multi-level, but at least as you will see, it will not require a high-end analog to digital converter. You can think of it as a A to D free solution. It works starting from the most important benefit. It can be operational in field. It can run in the background. It can operate in closed loop configuration. This test signal is spread spectrum. It has a wide excitation range. It has not, as you'll see, it doesn't have much impact on the noise, and it can be done only for brief periods of time. That way we don't cause much of a system noise. High accuracy. It uses circular cross correlation in order to extract the impulse response, and suitable for IC level implementation. It requires only a very simple linear feedback shift register based PRBS generator, random signal generator. It does not, theoretically, it requires a very low sampling rate, A to D, if it is required to be digitized. And one can even use the analog samples to extract the health of the system. It does not require much of a storage and computational memory. And it can extract the impulse response, which is the key parameter, from different injection points using, basically using correlation. So what's the difference between in analog versus digital? For a system under test, generating a response, digital correlation samples the response of the system and uses a DSP to correlate. It requires a lot of operations. In analog correlation, on the other hand, the correlator is analog domain, and it does generate a very low frequency. In very low frequency, it does generate the impulse response of the system to the A to D. For example, if it's a bandpass filter, in this case, we can excite the filter with a small perturbance based on pseudo-noise modulation, and use the circular correlation to get the impulse response, of which will be a certain attack and decay. And what you observe at the output of the analog correlator is basically white noise, followed by some kind of correlation output. The peaks are the samples of the impulse response. So basically, what you observe is between these little sticks, analog correlation is happening, and you're resampling at the end of one full period. So it requires n passes. If you want to have n points on the impulse response, it requires n passes, for example, and then you sample the peaks, and there it is. It's the impulse response of the system. And in most cases, within your low-pass bandwidth, you would be able to see this with ultimately close to the gold standard, which is AC analysis. And what else can we get out of this? We can ultimately we can get phase margin, because impulse, they overshoot. I'll come back to this in a second. The phase margin, Q factor, much of the stuff that we would get, damping ratio, much of the stuff that we can get from the impulse response characteristics has information about, let's say, maximum overshoot. So if there's an overshoot and ringing issue that's starting to show up, we can extract it in time domain alone. We don't need to go into costly spectral domain applications. They are all interrelated for second order systems. And after, I guess, 28 pages of introduction, now I guess we can get started with the proposed solution. This was an analog controlled DC-DC converter, mostly suitable for POL application, and I'll share the specification. It had an internal NMOS powertrain, and the PRBS sequences were basically injected at the PWM at VREF, meaning reference to output, and another injection point was in the PWM generator, which is inside the loop. So you can see that the perturbation points are one outside the loop and one inside the loop. One will go through a high-pass response characteristic suppressed at the DC. The other one will go through the closed loop AC characteristics. And the observation point is the feedback node, to be exact. Although we say the out, it's basically where feedback comes back in, which is a scale version of output voltage. With this, we hope to track phase margin, Q factor, natural frequency, center frequency, and we can use parametric model reference or non-parametric model reference because ultimately what we look at as a system, we know how POL should react to a load changes, and hopefully we have the baseline unaged version, or we have the baseline before we degradation begins, and we can track this. This is the linearized model. We can have two transfer functions. One is closed loop reference to output. This is the most common one, and the other one is loop response, which is disturbance rejection transfer function. In that case, the noise is not given outside the loop, but inside the loop, and that shows us basically the loop gain and loop suppression characteristics. And we observe as a linearized analog correlator at the output of the converter. And this is one level down, so to speak. How this is being done. As I mentioned to you, the pulse width modulation, pulse width modulator is basically a current into a cap, relaxation oscillator style, and we perturb the current into this cap for the inside the loop. For the reference, as I just showed in the bandpass filter example, we're basically going up and down around the set reference with small perturbation. At this point, accuracy of the measurement depends on a few things. How much perturbance can you afford to inject, which basically increases the SNR of the collected signal, as well as how long of a correlation can you afford, because every time we pass a pseudo noise through this converter, it requires that long period of a analog correlation function. The PRBS generator is, as I mentioned to you, is a linear feedback shift register. There are several codes that can be embedded for a preset and reset. And circular PRBS is a decoded version of it, because every time we pass, we need to generate the same code shifted by one clock signal. So this does exactly that. It generates, for the correlation, it basically generates a code, and it generates a shifted version. The same code basically is being generated with PRBS generator. In order to do the correlation, like I said, we need the circular generator, and this is a very computationally cheap hardware to do that. For the reference modulator, you can, this is VDD here, but you can think of it as a bandgap voltage reference in the middle. You can basically go up and down with the same code excitation. Represented as a DAC, but it's like basically a resistor string being controlled by PRBS. Again, depending on how much you can afford to go up and down on the string, allows you to increase the SNDR of the correlated signal by the expense of obviously higher noise at the output. This is how we do the pulse width modulation. Pulse width modulator, ultimately modulation, I should say, noise. We give a baseline current into a cap. This is like a relaxation of oscillator. And then when it's system identification mode, PRBS is being injected. And, basically we get minute deviation in the ramp, which changes the duty cycle ever so slightly for, like 6 switching cycles for a certain duty cycle and 6 switching cycles of a certain other duty cycle. Again, that's small enough that it doesn't change the dynamics of the load. The correlator, as I mentioned to you, one approach is to digitize the feedback system signal fully with oversampling, potentially oversampled A to D converter, and use a full-blown multiplier adder DSP-based correlator. And for a power converter, especially POL, that kind of digital complexity is very high, and it's not recommended. So we come up with an analog correlator, which is nothing but a switch capacitor integrator. PRBS clock comes in. Depending on 1 or a 0, we generate a +1 or -1. And then ultimately the multiplier is but nothing but a sampler. It uses sign, multiply, and accumulate. It's basically, as you can see, it's a workhorse in sigma delta converters, for example. It's like a lossy integrator where we reset after one full period of pseudo noise passing through. So the input signal is analog that we collect from the output, and the clock and clock bar are pseudo noise sequence that basically multiplies effectively by +1 or -1, and then accumulates. And at the end, once the pseudo noise sequence length is over, we sampled once. This is the red dot, and that makes up 1 point in the impulse response. So depending on how many points you would like to get, you repeat this thing. Depending on the frequency of the PRBS, you repeat this thing multiple times and extract the impulse response of the system, for example, from reference to output, or disturbance rejection from PWM to output. This is our test chip that was done in a more mature process. I believe at that point, this was requested by our sponsor. The BIST is mostly like less than 4% of the area, and it can be more compact if it's a digital intensive, if it is a digital fine digital process. And this is our packaged IC or open top unit. Now, you might be wondering why this is open top. At one point, we also, because this was being geared towards a harsh environment, we usually like to emulate single event transients that happens in high radiation environments, and to be able to shine a laser to emulate a single event transient. So part of it was an open top unit. This is our test board, in our lab, and I think our timing is quite good. Now a few slides on the performance. Now, first and foremost, how does the power spectral density get affected with PRBS internal? So the blue line is when the DC-DC converter is operational, V out. It has some, spectral content due to tones, PWM. When we enable the PRBS, around about 150 kilohertz, we get some pile up, but mostly a colored noise increase of about 20 dB below 400 kilohertz appears. This can be spread out further if the PRBS frequency is higher. And this is basically the spectral density of the V out without VC node injection. So without VC node control node. So this is the control, which is the VREF, by the way. And this is for the PWM. Again, slight increase in white noise will be observed. Now, we use PRBS frequency every 6th switching cycle. And this can be another variable one can use. You can use 10 cycles if your PRBS frequency is higher. Unlike Swept-Sine wave, you would not observe much of a tonal content. And that was spectral view. And here's the time domain view. We can see, the system identification enable versus not enable between from 22 millivolts peak to peak noise. Mostly we go up to a peak to peak of about 87 millivolts peak to peak. Again, this can be spread further if one can afford to run a longer PRBS sequence and wait a little bit longer. So the knob we have from accuracy trade-off point of view is how small perturbance you can inject, which determines your signal to noise ratio at the output after correlation, and how long can you wait ultimately. And this is some well-known math. How can we use the impulse response to extract several parameters? The peak value, maximum point of the curve. H of m is maximum deviation, at that point, at point m. First inflection point after m, and zero crossings. All of these have certain signatures. And here, the Q factor is a function of, ultimately R, Hi over Hm. So we can determine I point from the impulse response, and the Hi over Hm parameter can give us eventually the Q factor, and the Q factor eventually can give us phase margin. With this, you would not need a lengthy analysis. It does have some computational work involved, but lookup tables can also be used because it uses arctangent function. One can also use a quantized version of a lookup table. How does it look like? So this is our PRBS, solid PRBS, and this is our Swept-Sine wave, gold standard. As you can see, the PRBS, the continuous waveform, after we get the FFT of the magnitude from reference to output, quite closely tracks Swept-Sine wave at discrete frequencies. For a given number of cycles, we can basically extract peak-to-peak or a spectral response. Similarly, PWM to output also tracks pretty well with respect to the gold standard. Most deviations, sync-like deviations, happen at higher frequencies, which is, most of the time, is not that critical anyways, because much of our characteristics is extracted before these higher frequencies. And we can also, in a roundabout manner, we can also check on a load base changed, 50, 80, 150 milliamps loading. We can see the peaking change by using the Vref to Vout transfer function. PRBS tracks the change. Stability changes with with the load. We did not have a separate output current detector, but one can put an current sensor, either mirrored base, sense-fed base, or other methods, and correlate that with respect to the impulse response. So these are the Vref and Vout with different inductor values: 4.7 to 6 to 8 to 10.3, and capacitor values. Again, we're basically looking at the tip of the impulse response for different cap values as well. So with cross correlation method, with different inductor values, we can also kind of see 2 microhenry increments quite effectively, because you're looking at a few dBs of a difference at the output. And this is the PWM node to output, disturbance rejection, and these fall into model-based approach, where you have an expected value, and then you look for the deviations from that expected value from PWM to output. Left side is inductor changes, right side is capacitor changes, and some simultaneous parameter variations: cap, inductor, natural frequency changes. Here you can see it can operate in center frequency and natural frequency changes as well. Within our phase margin and closed-loop unity gain frequency error with respect to, again, gold standard is shown here. When the load changes, our extraction accuracy is somewhere around 2 to 5% range. Inductor changes, with a few exceptions, about 2% to 5%. Again, with capacitor changes, this is how our extraction for omega and Q and omega C is around 5-6%. So it can, at nominal operating conditions, it can extract. This DC-DC converter was not built for a state-of-the-art converter. It was still a decent converter, but our main hope was to implement the BIST, and these are our efficiency numbers with 5-volt output and 3.3-volt output. The most important thing is normal regulation circuitry is about this 0.5 milliamp, but BIST takes another 0.5 milliamp for about 12 milliseconds. The BIST circuitry power can be reduced in state-of-the-art processes as well, and can be optimized. This being a PhD thesis, we were a little bit more liberal in terms of the gain bandwidth of the amplifier used in the integrator. The rest is all digital anyways. And these are our peak efficiency numbers. And coming closer to 15 minutes to the hour, which I know that I need to be stopping. This is our performance highlights. Our input was 5 to 8 volts with 6.5 volt typical, 3.3 to 5 volt with close to 0.5 amp performance. And these are our BIST quiescent current and some of our detection performance. Phase margin is about 5.2%. Unity gain frequency around 4%. Natural frequency detection errors close to 4%. So as you can see, much of these BIST performance numbers are quite good. These are the conclusions. Impulse response is a gold standard. Swept-Sinusoidal method can be used, but it has tonal content. We use white noise to keep the average output voltage variation minimal, and the method can be implemented in the IC, and the output can be feeding to a host processor, or if the POL is in a bigger system on a chip, it can alert the system for future improvements, calibration. Future work could be certain FFT diagnosis AI, machine learning to extract the parameter changes. That way you can do non-model based estimations, because visually, when we look at the impulse response, if we can find out what is going on with the system, that means AI can do the same thing. And so rather than hard phase margin omega and omega C, we can train the system to detect certain pinpoint certain degradations like RDS on inductor capacitor by looking at the impulse response. And most importantly, I want to thank all my students who worked on this project. This was Navan Kurpevar's main thesis topic, and also in an LDO version of it was done by Kaushik Maladi. Maryam was on it. Dr. Kishan Joshi worked on this project as well as Debashish Mandal, who was the postdoc at that time. So this concludes my presentation, and I'll be happy to answer any questions you may have. In fact, I can go back to.
Thank you, Dr. Bertan, for a wonderful talk.
I won't stop sharing in case some questions arise from the.
Yeah, you can probably just keep the presentation on in case the audience.
I hope you can see the presentation still.
Yes, we can see it. Yeah. Thank you, Dr. Bertan, for a wonderful talk. I'm sure the audience will concur that this has been a very exciting and stimulating talk. So we'll get to the question and answer part of the webinar. So the first question is, what happens if a transient happens near or slightly after startup before the system has a chance to learn? Then the system's transient response might be worse near startup and cause the system to fail.
True. So what, in a nominal sense, this type of BIST algorithms would not perform well if there's a transient response. So if during the, usually it assumes that the load is at steady state within a margin. If a transient is detected while the PRBS algorithm is running, that estimation should be purged and started again. Unfortunately, that's one shortcoming. It requires some kind of a steady state operation, or maybe when the load is still on, it doesn't matter, load can be on. But for cases where large transient are frequent and it can be coming in at any time, this approach might be problematic. So for large and continuous transient approaches, this may be problematic. Or alternatively, again, this is where AI can come into the picture. If one can detect the transient characteristic and train the sequence on how the impulse response would look like during transient operation, system parameters can also be extracted during large transient situations. But it won't be as simple as a Q, omega, and omega C phase margin type of a thing. It will not be as easy. That's a very good question.
All right, thank you. And so the next question is there any limitation for implementation in different types of, different topologies of DC-DC converters?
Yes, if it's hysteretic, because, and not frequency synchronized hysteretic, it needs a little bit more creative perturbance injection. Right now with PWM, we can synchronize it with PWM cycle. We don't need to know what the PWM duty cycle is, but during one full period, we can basically, let's say, inject 6 or 8 chips. These PRBS bits are sometimes called chips. We can inject these random things, but for hysteretic, because the duty cycle is like an accordion, it may require us to be a little bit more creative, or maybe do asynchronous. So that will be one shortcoming. However, for current mode control, it's non-issue. We can in fact inject quasi current mode feedback. We can inject to that node as well, or observe from that node as well. In fact, it will be a very good application area to use it on a current mode controller. I can't think of other control. This can be used in a boost converter. Again, because it's ultimately reference and PWM injection, advanced duty cycle injection, which can be used for right tempo A0 tracking as well. In that case, we have done it although it's simulation, we've done it on LDOs. LDOs showed excellent result. I mean, if, for example, ESR is degrading, phase margin is changing, this can work in an LDO. Only downside is LDOs tend to be smaller chips, and obviously they need to be quiet. That's why we use an LDO. Because the load is most probably sensitive, one may not afford to have too much of a noise on the power supply. But if it's during off times or when there's a load transient, or when it's a known period that the system knows to go into self-diagnosis mode, LDOs are also good. I hope.
I think a related question to that is, does this technique also work in switched cap converters, given the measurement mechanism?
That's a good one. So in a typical charge pump switch cap, ultimately what parameters could we use to extract? I believe the switch are on and cap, maybe absolute cap value degree of, let's say, flying cap and a load cap, and this thing is running. For example, Kishan, what would you like to extract in a switch cap? Then maybe I can try to answer in return. For example, RDS on of the flying cap, the switches that control the flying cap may be extracted, for example.
Yes.
Usually stability concerns are minimum, and it operates kind of small signal. So I think that's what that comes to my mind. Can you think of anything else?
Yeah, I think that's probably what you meant. The RDS on and the stability, the phase margin of the loop. Yes. All right.
Yeah.
Okay. So going to the next question, how does the accuracy of the BIST vary with lower magnitudes of PRBS and also across temperature and...
The first portion, the audio broke up, Kishan. Can you start?
Sorry, how does the accuracy of BIST vary with lower magnitudes of PRBS and also with the temperature and the cap quality, measurement cap quality?
Yes. So you can think of it in a way that you either elongate the PRBS or increase the amplitude. If one can afford to elongate, you can practically push this below noise floor. As most of you are aware, GPS signal is PRBS and it's below noise floor, and we can get location fix within a few minutes. So the way it operates is basically it correlates for a longer period. So I don't find the amplitude as that much of a shortcoming, but for a given duration of a PRBS sequence, it linearly tracks. Basically dB per dB, your SNDR after correlation would change, ultimately. But you can overcome that, like I said, if you can afford to run it for a longer period. What was the second portion, Kishan?
And also the dependency of accuracy on the measurement, on the cap quality and the external temperature per se.
Temperature, yes. So if there's, so ultimately, if there's any changes, let's say on RDS on, the threshold voltage, or if it's an analog compensator in the feedback loop, if there's any gain bandwidth change, this will detect it. So if one can have a small temp sensor, again, this is an approach that one can use. Hey, I'm at room temp, or I'm up by 20%. Then you would know that this is changing. Some of these parameters are changing because the temperature is changing as well. So temperature can go into the model reference, one of the model reference parameters, just like iLoad. average load versus temperature. But the key is at, let's say, 40 degrees junction temperature. A month ago, we were getting this response. Then you can correlate it. Now we're getting this at that temperature. So there has to be some changes. That's, is basically reference-based degradation. As time goes on, you can correlate at that same temperature, same load, what has changed, type of a deal.
Right. Okay. All right. Thank you. So the next question is how to differentiate the spectral content due to EMI and PRBS generated BIST loop or single event effects in radiation environment.
Excellent point. Now, as we cross-correlate, so let's assume the feedback signal has certain, obviously it will have ripple due to DC-DC converter, output ripple, and it will have load, sometimes load-related, impulses and stuff. Let's assume we have nothing but that. We do not have any PRBS injected. Yet we run the correlator. Now, input is typical load-related, typical current-related output ripple, PWM-related output ripple, and load-related load transients. Now, as we pass this through the analog correlator with PRBS, white noise, the output will be completely whitened up. So it may be a tone coming in, it will be probably smeared out in spectral content. So it will have a bunch of discrete tones in spectral domain coming in. Once we correlate it with a pseudo-noise, output becomes pseudo-noise. I hope this makes sense because that's the key point. Anything uncorrelated passing through a white noise-based correlator will generate white noise. So it will become floor noise. That's the best part of this. But if it's correlated with your PRBS, which is indeed what our injected signal is, output will look very meaningful, especially within the impulse period. So, for example, here you can see before and after, it's still looking like white noise. The reason is it's basically correlating uncorrelated signals. So during these periods, there can be, this is a bandpass filter, so it doesn't have any tonal content, but during these periods, there can be impulses in time domain. There can be load changes, ripple. You will not even see it. It will be completely smeared out. I hope I make sense.
Right. Yeah.
But, in theory, it will limit your SNR, but during at least the main attack of the impulse, it will look pretty clean.
Okay. Yeah. Thank you. So the next question is there a difference if an isolated converter is used with a secondary controller in terms of the application?
Excellent. So if we we can embed, that's a very good question. So it does require a synchronized correlation engine. So if we excite the system in the primary side, non-isolated side, on the isolated side, somehow we need to generate, I assume we don't want to do any other path between the isolation barrier. I mean, if one can do even a single cap-based start signal to the isolated side, to start the correlation, even the clocks needs to be synchronized. So I'm curious, that's a very good point because one would like, you can do reflected maybe. You can excite the system from the primary side and, like any transformer, the response of the secondary side will respect to the primary side.
Right.
Maybe in a roundabout manner, one can try to track the, for example, transformer and secondary side characteristics by observing the primary side.
Right. Yeah, that's an excellent point. Yeah.
Do you think it can be done? I mean, does it make sense?
Yeah, I think it makes sense. Yes.
From power converter point of view, I did see some approaches where they use primary side fly buck is like that, right? I mean,
Right.
flyback is basically primary side is a buck converter and transformer coupled to the secondary side, and we
Right.
regulate from the primary side in flyback.
Right.
They're low power isolated, but not high power. But
Sure. Okay. All right. So we'll take two more questions, and then we are nearly out of time, so we'll close after that. The next question is, what kind of bandwidth will this technique be practical for? And do you need to limit the PRBS bandwidth really for that?
yes. So as you can see, the PWM frequency times 6 is what we have used. So for a converter, now it can be 8, 10, and it will spread it. You just need to run the correlator slightly at a higher and higher frequency. So this was a 5 megahertz converter. One of the goals was to enable smaller output components. So you can see about for a switching frequency, we're basically we have some room to do the cycle modulation. I can, in state-of-the-art processes, I don't see frequency as any limitation, because ultimately we don't need a full-blown A to D to sample the response of the system with oversampling. So I can easily say 10 to 20 megahertz is possible in terms of unity game bandwidth, or crossover frequency characterization.
Oh, all right. Yeah. Thank you for that. So the last question is, are there any issues using this method for a multi-output system?
These are all excellent questions. For a SIMO, that's our audience gave me so many interesting ideas. I especially isolated, and this SIMO would be great. Depend on, so in the SIMO case, I do know that the cross regulation is a big issue, and we all know that. But especially if it's not done right, the last when the last if it's not DCM mode, if it's going CCM, the last guy channel. I don't want to make any claims, but the last channel tends to get the last chunk of charge, and sometimes it gets harder and harder, if I'm not mistaken. I'm not an expert in SIMOs, multi-outputs. I presume the question was on a SIMO, right? Not a...
yes, yeah, a multi-output system. Yes, yes.
If I have to apply this, I think it may be a good one to apply on cross-regulation, degradation detection. How it can be done? One can use, let's say, 4 output. One can use 4 distinct PRBS signals, and because they are uncorrelated, one can detect, their signature at the output, individual outputs on the SIMO case, and that may have some valuable information about the transfer function for channel 1, 2, 3, 4, and based on that, maybe duty cycle can be changed to equalize their response. That's a very good question. I think it's a excellent application. I'm sure there might be some value out of that in a SIMO.
Sure. Yeah. Right. Thank you for that, Dr. Bertan Bakkaloglu, and thank you for addressing so many of the audience's questions. We had a wonderful webinar, and thank you for presenting this.
Thank you.
And I'd also like to thank our co-sponsors, the PELS Milwaukee chapter and the UC Berkeley PELS PES IAS student chapter. Thank you all for attending the webinar and for your time today. Thank you, and have a good one.
Appreciate it.
All right.